So our next speaker is Avrim Blum from CMU. Avrim is one of the pioneers of the connections between theoretical computer science and learning theory. And he's been working on questions looking at that perspective of learning theory in algorithmic game theory since the beginning of algorithmic game theory. In particular, he has work relating no-regret learning algorithms to equilibria, correlated equilibria in games, and understanding the first paper that sort of looked at what were the consequences for the quality of equilibria if people are playing by learning algorithms instead of playing in the more conventional Nash or Bayes-Nash equilibrium. He also has been some of the very early work applying ideas in learning theory to mechanism design. And on a personal note, he was my postdoctoral mentor. He was also Aravindan's postdoctoral mentor. And he's been actually a fantastic mentor to many, many of our fine young theorists in working in algorithmic game theory and learning theory, et cetera. And I think, even in fact, he has some academic grandchildren in the audience here from Madison who are working with Shuchi Chawla, who's also his PhD student. And so it's really great to have him here talking about what he's doing currently in this space. Thanks, Avrim.
Yeah, thanks for that introduction. Actually, I learned about mechanism design from Jason. I remember when he was, I guess, finishing grad school and giving talks, and we were all trying to figure out what this stuff was. And then I had a chance to work with him, which was great. And we had an early paper on learning and mechanism design. It was really a lot of fun and trying to combine these different concepts together. And it was really a big learning experience for me, and it got me into this area. So I really thank Jason for that. And so it's great to be here. See a lot of old friends, too. So I'm going to be talking about reconstructing preferences from opaque transactions. I'll get to what that means. This is joint work with Yishai Mansour at Tel Aviv University and Jamie Morgenstern, my former PhD student, now at Penn, also the same Jamie from the last talk. All right. So let me start. So a very classic problem. Given random samples of some function, try to learn a good approximation to that function. Okay? So this is basically all of machine learning, or not quite, but okay. So this kind of a problem. Okay, fine. So it's very classic, a lot of work. A less classic, but still pretty well-studied problem is given random observations of some agent's actions, see if you can figure out what that agent is trying to optimize. All right, this is, I think, a really exciting kind of problem. And there's work in the machine learning world called inverse reinforcement learning that kind of does this in a Markov decision process framework. In the economic setting, it's often called learning from revealed preferences. So you see what the agent buys, and you're trying to figure out from that what they want. There's a lot of really nice work on that. So what I want to talk about today is suppose you don't kind of like that, but you don't have access to the agents in isolation. Instead, all you get is the result of observing some multi-agent interaction. These agents get around in some smoke-filled room, and out comes something. And you want to do is, can you, from observations of this type, reconstruct the agent's preferences? All right, and I want to talk about this in a couple of contexts. So from observing the outcome of a series of auctions, just who won, like which ad, you click on the page, you see an ad, so they won. Okay, so from just seeing who won, can you, many times, can you reconstruct agents' preferences from observing the outcome of a bunch of auctions? Or from observing which agents end up happy and which not in some allocation process of allocating resources, can you try to reconstruct both the agent preferences and the resource allocation mechanism from observing this kind of thing? All right, so that's the kind of problem I want to talk about. And I'm going to talk about a couple of simple problems in this space. All right. So I'm going to look at two models at the high level. So let me give you the high level here, then we'll dive into each of them. So the first is, imagine a repeated auction. We have a collection of agents. Each one has has a valuation drawn from their own distribution of values. And okay, so there's their valuation. But you don't see these. All you can see is who wins. You just see who wins the auction. All right? Pink won. You can also participate yourself. So you can bid. Maybe you'll win, or somebody else wins. And your goal is from the repeated scenarios of this type, where each time you imagine is fresh draws from the distributions, you'd like to recover what these distributions are. All right, that's the problem. The second setting I want to look at is one that's going to be in some ways harder. I want to think of a combinatorial auction. There's many items with agents with combinatorial preferences. But we're going to think of things simpler. The agents will be deterministic. There'll be simple deterministic things like single-minded, unit demand. I'll talk about these later. These preferences are unknown, but they'll be deterministic, and that'll make it simpler. And also the auctioneer mechanism will be from some family, but unknown within that family. And our goal is going to be to recover the preferences and the auctioneer's mechanism. We're going to look at priority-based mechanisms, and I'll tell you what I mean by that. All right. So actually, just to kind of dive into one thing, I'm going to talk about this direction first. It's a little bit cleaner because there's no probabilities. Consider the following scenario. Okay, so I'm just going to dive into one here. Imagine there are n bidders. So here are n bidders. And there's one auctioneer. Okay? And each day, some subset of the bidders participate. And this is going to be, they're going to be single-minded bidders. So we're going to imagine that they each have a demand set. There's some resources. I like to think of them as jobs that maybe they have different resource demands, and they might overlap. So if they want to be scheduled today, but they can't necessarily all be scheduled because one might need these resources, other ones might need those resources, and they overlap. So it's jobs that want to be serviced on some machine, or lobbyists, I like to think of, who want to be serviced by a politician. And any resemblance to any current politicians is completely coincidental. All right, so every day some subset of the bidders participate. So not all of them every day, but each day it's some subset, S sub t. So S sub t participate. They go in, and out comes some of them end up happy and some of them not. Okay? So these jobs got scheduled and that job didn't. These lobbyists got what they wanted, that one didn't. Okay? And right, so like I said, the bidders have demand sets. The mechanism, we'll imagine, has some priority ordering over these bidders. I'll get to what I mean by that in a second, but some ordering that's going to do to allocate the resources to the bidders, unknown to us. And our goal is going to be from this to try to reconstruct the unknowns from our observations, or at least be able to predict well when a new set goes in, which ones are going to end up happy and which ones are going to end up not happy. All right, that's going to be the scenario. Let me just say it again now a little more formally. It's going to be binary here. Yes, visible. It's available to you as a... Yes. So let me just say it again a little more formally, but still with funny pictures. So there are n bidders. Every day t, some subset of the n bidders show up. There are m items. We don't get to see the items, though. Every bidder is single-minded. So these could, like say, this is a pink bidder, blue and green. They each have a different subset. This is their demand set, what they need. These could be the resources that the jobs need to run, something like that, or the things the lobbyists wanted. But they're single-minded. The mechanism has a priority order that we don't know over these bidders. It's maybe like how much they paid or their priority of the job, something like that. What we observe is each day we get to see the set that shows up that day, and we see who ends up happy and who ends up not happy. Okay, so for example, notice there's a kind of non-monotonicity here. If blue and green showed up, blue would end up happy and green would end up not happy because they overlap and blue has higher priority. So if blue and green showed up, the mechanism, what does the mechanism do? The mechanism just goes in this order and allocates in a greedy way. Okay, so the mechanism is going to say, look, so if blue and green shows up, blue will get what they want, green won't because they overlap. But if blue, green, and pink show up, then green will be happy because pink will get what they want, blue won't. They won't get scheduled, and then green doesn't overlap with pink, and so green will be happy. So we'll see the set show up, we see who ends up happy. The next day, a different set shows up, we see who ends up happy. Our goal will be to predict, given correctly on a new subset of bidders, and our learning, the way this is going to be phrased in what's called a mistake-bound model of learning. Our goal is just to make a limited number of mistakes, where our goal is a polynomial and many mistakes. So there's an exponential number of possible subsets. Obviously, we will no reason to make more than 2 to the n mistakes, since once a particular subset shows up, we know what happens there. We can remember that. But we want to make only polynomial and many mistakes. Okay, so that's the set. Right? So to think about this, let's look at a simpler problem. So let's make this problem simpler. So we have a bunch of items. Let's say there's only one item that everybody wants. And let's also simplify further by imagining that every day only 2 people show up. All right, so that's a simpler problem. Actually, for the simpler problem, n squared is now boring because there's only n squared different pairs. Okay, so what you would want for the simpler problem would be to beat the n squared, which you can do. And so what does this problem look like? So every day 2 bidders show up, say blue and green, and they both want it. Who gets it? The higher priority one gets it. So the blue is happy and green is unhappy. And if you think about this problem for a little bit, you'll realize this is like an inverse of the usual comparison-based sorting problem. In comparison-based sorting, there's some unknown ordering of items. You, the algorithm, pick 2 items to compare. An adversary tells you which one is bigger, because they have the ordering, and you're trying to make as few comparisons as possible. Here, in this problem, the adversary picks the pair. You have to guess which one is larger, and you're charged 1 every time you make a mistake. And your goal is to minimize the number of mistakes. And the reason I say this is really like an inverse is that there's a good algorithm for this, actually, which makes only n log n mistakes. And it's very much like a computationally efficient version of the usual sorting lower bound. So how does the usual sorting lower bound work? In fact, so what is the algorithm here? What do you want to do in something like this? When green and blue show up, given all your past history, one reasonable kind of algorithm is look at all the linear orders in the world that are consistent with the previous outcomes. Out of all of them, put them into 2 buckets, those in which blue is above green and those in which green is above blue, and predict whichever bucket is bigger, because that way, if you make a mistake, you get to throw out the bigger bucket. Now, the only issue there is there's n factorial ordering, so you don't want to be going through them, but you can efficiently sample, so that there are algorithms for efficiently sampling linear extensions of partial orders, and from efficient sampling, you can start estimating which side is bigger and go with that. And so you can solve this in a computationally efficient way, making about order n log n mistakes. So just an example. This is the case of one item. All right. So now let's go to the case of lots of items. Now here we're not going to be able to get n log n. There's an n squared lower bound, but we'll be able to get n squared as an upper bound as well. Okay, so we'll be able to get tight upper and lower bounds. So again, we have a bunch of items, single-minded bidders. And the idea is, rather than trying to learn the subsets, since we don't actually get to see the items anyway, we just see who's happy and who's not, let's just try to learn the conflict graph that says which bidders conflict with which. So the thing with single-minded bidders is 2 bidders either conflict with each other or they don't. Do their sets overlap or they don't? Like here, green and blue overlap, blue and pink overlap, but pink and green don't overlap. So we can kind of describe the scenario with a little graph like this, with an edge between 2 that conflict with each other. And now, at the same time, we're going to try to learn this at the same time as we're trying to learn the mechanism's ordering over the bidders. And so that's going to be our job. Right? And In fact, actually, but before, I just realizing in watching Tim's talk, so another way to talk about this is imagine that you have a graph, but you don't get to see it. There is an unknown weighted independent set algorithm from some priority family that has some ordering over the nodes, but you don't get to see that either. What you see instead is you see a subset of nodes. You don't get to see the edges ever. You see the subset of nodes, and then you see which nodes the algorithm chose. Then you see another subset of nodes. You see which ones the algorithm chose. Those are the ones that are allocated, the goods. And your job is, to try to predict, given the new subset that shows up, which nodes are going to be chosen in this independent set, the set of things that can be allocated goods. Yeah? OK. So. So we're going to keep these two separate. So this part of the graph just corresponds to the bidders. So the bidders themselves are single-minded bidders. They have sets that overlap. And so we can describe this, just the bidders, in a graph. So this graph just describes, if you look at which bidders overlap and which ones don't. Then there's a mechanism. So we're just going to keep these separate. So we're going to try to learn these two things separately. You could motion them, but we're going to keep them separate. There's an ordering over the nodes, which we don't know, and there's a graph that describes the conflicts that we don't know. When you put these together, you do indeed get directions. But let's keep them separate from to think about them. Is that? Okay, good. Yeah.
So here you're looking for efficient computation efficiency.
Yeah.
Suppose you didn't care about computation efficiency. Is there like a bound that's easy to?
Yeah, in that case, you could, if you didn't care about computational efficiency, then things would be easy in the sense that there's only 2 to the n squared kind of graphs and only n factorial orderings, and you could, so there's only that times that many pairs, and always predict based on majority vote and do that. But we don't want to.
Yeah. So n squared is the right.
Yeah, and you can do, that's right. And you can get actually an n squared lower bound. All right, good. So let me give it. So here's an algorithm that actually reaches that. So it gets tied up to constants. We'll start by assuming they're all in conflict. So these are all the bidders. They're all in conflict. We don't know. For sure, whatever the correct graph is, it's a subgraph of this one. And we'll start with all the bidders at the top of an ordering. So actually, for now, instead of thinking left to right, think top down. So we're going to have a set. These are all in an equivalence class. They're all at the top of ordering, and this will go down. So lower down means lower in the ordering. OK, so we're going to all together. They're all together at the top of the ordering. And now we're going to predict using our current who wins, using our current conflict graph and an arbitrary linearization of our current partial order. We'll use that for prediction. So given a set that shows up, who wins? OK, so now here's some easy things we can do. Imagine that the correct answer someday includes a pair that's connected by an edge in our graph. Like, let's imagine that these three show up, pink, blue, and yellow pink and yellow both win. Well, our graph had an edge between pink and yellow. Well, clearly, they can't conflict. Otherwise, they wouldn't both win. So we know that edge was a mistake, and we can delete it. So if this happens, if the correct answer actually includes a pair connected by an edge, we can delete it. We're making progress. That's going to happen at most n choose 2 times. So that's great. So we can just delete that edge, and we've made some progress. We're still a superset of the correct graph, but we've gotten rid of an edge. So that's great. We've made progress. All right. But it could be that the correct answer doesn't include a pair connected by an edge, but nonetheless, we made a mistake. All right. So like maybe, for instance, green and pink show up, and green won and pink didn't. So that's not a, and we predicted pink would win. So we made a mistake, but it's not because there was an edge. But then, like in this case, it's very easy to see, since they're at the top level, oh, well, if green won and pink didn't, it must be that pink is lower down the ordering. And so we can safely demote pink to the level below. Now, this is easy to do at the top level. It requires some argument when you're below there. But it turns out that you can show that as long as you only update on your first mistake. So in particular, what I mean is first, if there's an edge in the conflict graph that shouldn't have been there, you just do that. Otherwise, you just go down your partial ordering until you look at the first mistake you made. So if you make a mistake, if you don't make a mistake, you don't do anything. But if you made a mistake, that the very first mistake will have to be, and this uses the fact that your conflict graph is a superset of the correct one, it'll have to be a scenario where you thought someone would win and they really didn't. And the reason is because they must be conflicting with someone at that level, but so they're below there, and you can actually put them down. And you can guarantee that, so every mistake you push at least one guy down by at least one step, and you can guarantee that you will never demote anyone below their current place, their correct place. You'll never demote anyone too far. So this guarantees you'll make at most n choose 2 mistakes in deleting edges. Every mistake deletes at least an edge. Or at most n choose 2 mistakes that cause a demotion, because nobody's demoted below their correct level. And so somebody's demoted 0 times, a 1, and then a 2, and a 3, and a 4, up to an n minus 1. So n choose 2 there, n choose 2 there. And this overall will make at most n squared mistakes, which is optimal. Order n squared mistakes. OK, so that's an algorithm for this case. Yeah.
Are you getting only pairs arriving in this?
Oh, it could be a subset, a subset. Yeah, so some subset will show up. And what you'll do, so the algorithm for predicting will look at that subset, and then it'll just arbitrarily linearize this partial order and just go through and just act like the mechanism under that order, just saying who wins. And then if you make a mistake, you'll go through and say, do I get to delete an edge? In other words, did 2 people win that I thought were a conflict? If so, I delete that. Otherwise, I go through and find the first place I made a mistake. And wherever that is, you use the fact that you didn't make any mistakes above there, and this is a superset to say, OK, I can actually demote some guy. But it could be, yeah, it doesn't have to be 2. Right. So there's 2 to the n possible subsets, or minus 1, that could show up, and but only n squared mistakes. All right. So that's this case. Yeah, and so you can also apply this to cases where the conflicts don't come from items. They could just be conflicts. It could be, you have, say, banner ads, and some subset of advertisers want to show a banner ad, but they don't want to be shown with a competitor from the same industry. So maybe, Toyota and Ford don't want to both, be on the same page, or and so they might have a conflict. So it doesn't have to necessarily come from items. It could be any kind of conflict. All right. You can view conflicts as virtual items if you like. So, yeah. OK, so now what about unit demand? So let's look at a different scenario. I'll use the same picture, but now with different meaning. So let's say the bidders have subsets of interest again. So you want to buy a toy for your kid, but they just want one. OK, so they have a subset that they care about. These would be the toys that are reasonable. They just want one, maybe like this. And they have a preference ordering over their demand set. So pink, maybe these are the 2 reasonable toys for their kid, and maybe this is higher than that. Maybe for blue, this is better than that, and for green, maybe this is better than that. I feel like we don't really need to talk about subsets. They could just have an ordering over everything with some items of value 0. They wouldn't want even if they were there. And each one will take the highest that's available. OK, so the mechanism now, again, there's still the seller has an unknown priority over bidders, allows them to kind of walk into the store in that order and take their highest priority thing they want. So that's the mechanism. The mechanism, it just has this ordering. The platinum elite gets to go first, followed by the gold elite, and then the silver and so forth, in terms of what they get to pick, which seat they want, or whatever it is. And yeah. OK. Now for this, let's say that you get to see what they come out with. So you get to see who gets the jack in the, if they come out with the jack in the box, you get to see that. If all you see is did they get something versus nothing, this turns out to be a computationally hard problem you can show. But let's say you get to see what they come out with. OK, so you get to see, who came out with what. Again, a subset comes in, you see what they come out with. And what you're trying to do is figure out the ordering and what the bidders ordering over items, and the auctioneer is ordering over bidders. OK, we want to figure out what will happen on a new set. All right, so it turns out you can solve this by reduction to the previous case. It seems really different because this is like a single-minded. It's an OR. And this is a unit demand, which is an OR, and single-minded was an AND. But nonetheless, you can do a reduction in the following way. For every bidder, create m copies of that bidder, one for every item. So we now have a copy, a bidder-item pair, right? And now we'll say that two copies, two pairs, bidder comma item, are in conflict if either they correspond to the same bidder or they correspond to the same item. Because no two in conflict can both win, right? A bidder is not going to take two things, and no two people can take the same item. So we have n times m virtual whatever bidder item pairs, and we have a conflict graph unknown. And now the ordering over bidders and the bidders ordering over items, if you sort of flatten all that out, that becomes an ordering over these bidder item pairs. And now observing who gets what in this scenario corresponds to observing which of those copies ended up happy and which didn't in the original problem. And so you can just by reduction, it's going to be this thing squared. So it's order n squared m squared mistakes total. It's just this many squared. That was from the previous. All right, so we can do that. Now, you can actually do a little better. So that's n squared m squared. You can do it more efficiently by combining this with that inverse sorting idea. So it turns out you can use that inverse sorting algorithm for learning the bidders' orderings over the items at the same time that you're using the previous kind of pushing things down method for learning the auctioneer's ordering over bidders. And if you put those two together, you can save a bit from n squared m squared down to n squared m log m. So one of the m's went away and became a log, so you can save that. You can get a lower bound that's 1 factor n below that, and that's not too hard to show. And it's unclear where the right answer is between these two. It would be nice to use the inverse sorting kind of idea both on the bidders ordering over items and on the auctioneers ordering over bidders, but it doesn't seem to work. They just interact with each other badly. So I don't know where the right answer is, but somewhere between there and there. All right, so that's an open question. All right, so that's right. So now we can also extend this. So what about their prices, right? So what kind of made every day different was every day was a different subset of people that showed up. That's what made day 7 different from day 3. It was a different set of people. But we can also add another factor in here, and actually doesn't make things too much worse. What if every day is also different, perhaps in that there's different prices? So each day there's some vector of prices. And now, in addition to there being perhaps a different set of bidders that showed up. And then we could again say, what if bidders are, for instance, unit demand? So what do? Each bidder has, let's say, a value on each item. And they just say, I have a value on each item. There are prices on the items. I take the item that maximizes value minus price. Or I take nothing if these numbers are all negative. Or you say even simpler than that could be just additive. The bidders, again, have values on items, and they take all the things whose value minus price is non-negative. Okay, and again, there's a priority ordering over bidders. Oops, priority ordering over bidders, so that the auctioneer, okay, the platinum select gets to go first, take the things they want, and then the gold, and then the silver, and so on. And again, you can use the same idea, maintaining a partial ordering of bidders, where each bidder is at some level and no one gets pushed down too far. And however, the other part, on incorrect prediction, what you can do is, again, you look at the first mistake in your ordering. What that will do is it'll add in a linear constraint. So you're going to try to solve for the bidder's values, and every mistake will give you a linear constraint you can use for that bidder. And so you can, you can view it like a separation oracle. You're going to have a convex, currently believed feasible region for that bidder that describes what their possible values are on the items. Every time you make a mistake, it's going to be a separate. You're going to have a, maybe some proposal from there. It'll give you, a separator, something that separates what you thought it was from the correct answer. And then what you can do is run a linear programming algorithm that works with the separation oracle. Let's take ellipsoid, for instance. And then once that thing, the feasible region becomes empty, you realize, oops, and then you knock them down a level. So they have the certain levels, and then you're going to do this and realize the analog of making a mistake before will be their feasible region became empty, and then boom, they go down a level and you restart. And so that's the way the algorithm is going to work. In the case of additive bidders, it turns out you don't need all that complication. The decisions are separable. The LP is just one-dimensional binary searches. It's linear programming in one dimension, so it's like a feasible region. You can take the middle. It's not too hard. It's just binary search. That's what binary search is. And then, oops, separation oracle takes the middle, and so on. And so that works nicely. But in the case of the unit demand, it looks like you need a general linear programming algorithm. Number of mistakes is n squared demotions times the mistake bound to the linear programming algorithm, how many separation oracle calls it needs. OK. So that was...
With your comparison to binary search, you're not setting any prices. You're just observing what's happening.
Right. Good. So yeah. Right. You're not setting prices. What you're trying to do here, is I'm trying to guess what the bidder's values are on different items. So what I'm doing here is I'm making a guess. I think this bidder, and what I really have for each bidder is a range of possible values that they might have on each item. And I'm going to guess the midpoint of that range. And then what you can show is that when you make a mistake, you can take for each, for at least one bidder, for at least one item, you can chop that range in half. That's all. And then you have a new guess as to what their value is. Good.
Must we assume that there's no learning possible? The bidders don't change their bids?
Oh, yeah. Well, OK, good. So the assumption, I guess there's two parts to this. The assumption is the bidders are stationary. Their values don't change. The mechanisms we're looking at are all incentive compatible. They just order the bidders by some external thing, their status, and just let them enter the store in that order and then buy whatever they want. So when they come in, from the bidder's point of view, they're just saying, say they just want one toy, at the current prices, which item will maximize value minus price? So I guess what I'm assuming here is that the prices per day are something that happens the bidders have no influence on. So they can't strategize, oh, maybe I'll pretend I don't like this. That'll affect tomorrow's prices. I'm kind of viewing the prices as just externally determined. Yeah. Yeah. Good. Good. All right, so now let me switch to this Bayesian model. So the Bayesian model, so let's make the problem easier. There's just one item. And the auctioneer sells it to the highest bidder. So simple mechanism. We know what it is. There's no question about that. Maybe they sell at the second highest price, Victory auction. But we don't see the prices anyway, so it's not going to really matter. But let's say it's incentive compatible. It sells at the second highest price. So here they are. Here are the bidders. They have their bids. But what's going to make this harder is that the bidders are stochastic. This would be easy, actually, if the bidders always bid the same thing every time they show up. We would just try to figure out that order. But what's going to be harder here is the bidders are stochastic. Each bidder has, on day T, if they happen to show up that day, their valuation will be drawn from their own personal distribution of values. So this is a distribution over numbers, over say the range 0, 1, or some range. Their value will be drawn from that distribution, and then so that's going to determine these things. And then the next day, it's independent draws. OK, so this is going to be the problem we'll look at. And we just get to observe the winner. So we get to observe the winner. So we don't actually see the values, but we can participate ourselves, and we want to learn what these distributions look like, at least best we can. So let's just think about this problem for a minute. So some difficulties. So let's imagine actually that we see the winner. So what do we have here? Just mathematically, what's going on is we have, say, 4 unknown distributions over some range like 0, 1. When you press the button, independent draws are drawn to these distributions, and you get to see the argmax, the index of the maximum. And let's say you also get to see the max. So you get to see the index of the maximum and the value. So you press the button, and you see, bidder 1, and it was 80 cents. Press the button again. Oh, now it was bidder 2, and it was 73 cents. OK, that's what you get to see. So let's imagine we get to see the winning bid. So we get to see who won and what they bid. But the thing is, it's not a representative draw, because you're seeing it conditioned on them winning. So it's not like when you see bidder 1, it's not a representative sample. Okay? So it's like, for example, just to be concrete, let's imagine that they were all the same distribution, uniform in 0, 1. Okay, the maximum is not uniform in 0, 1. If you have n bidders, the maximum of these n independent uniform draws from 0, 1 is very likely to be somewhere in this range, or pretty close to it. The distribution on the maximum is not going to be uniform in this range either. It's, it's going up. You can integrate it out if you want. Right? So it's so if you look at your data conditioned on seeing bidder 1 win is not, they're not draws, IID draws from D1 because you're conditioning on them being the maximum. And what we want to do is extract out what these distributions look like. Now, there is an issue that at the low levels, you're never going to figure out what things look like. Okay? So, in fact, let's just define P sub epsilon to be a price such that the probability the winning price is below this is epsilon. So, for example, if these are uniform draws in 0, 1, it's very unlikely the winning bid is going to be like a half or much less than 1 minus 1 over n. So there's no way we are going to really learn what the distribution looks like below there because we never see wins below there. We might be able to figure out how much probability mass there is below there, but not how it's allocated. Does that make sense? So kind of below, this is the range we'll be able to figure out hopefully what things look like here. Below there, we'll just know like how much probability was there, but not whether it's all sitting at 0 or it's sitting at a half or whatever. Since they never win there, we'll never know. So our goal is going to be to above P sub epsilon to try to estimate the distributions. So we can really only hope to learn them above there. So it turns out there's a really useful tool for this, which is called the Kaplan-Meier estimator. It comes from medical statistics. It's a great tool. And that, in essence, solves a version of this problem. Okay? And it's a really great thing. So where Kaplan-Meier comes from is imagine you're doing a study of survival rates after some medical procedure. Okay? But the problem is patients keep dropping out of the study. All right? So you're trying to figure out how long they lived. You call them up. They don't live. They're not there anymore. They keep dropping out of the study. And you want to still get good statistics. So this is what, this came out in the 1950s or so. And so the model here is, let's assume that each patient T lives some number of years, x sub t, drawn from some distribution D1, which is the distribution of how long someone is likely to live after this medical procedure. And they would drop out of the study y t years drawn from some other distribution of how long people are likely to stay in the neighborhood before they go somewhere else and drop out of the study. And you see whichever comes first. Okay, you get to see which of these two events happens first. And we'll assume they're independent of each other, independent draws. So an xt and a yt are sort of independent random variables, and you see whichever one happens first. And your goal is to recover this one. This is the one you care about. You don't really care about the other one. Up to the point where pretty much everyone has dropped out of the study, so you don't get good statistics anymore. Right? That's what your goal is, to try to recover that. And so let's assume that no two events happen at the exact same time. Right. So there is an issue. Yeah. So maybe it's a coin flip. Yeah. Good. And the idea in the Kaplan-Meier actually is something very natural to do, which is you're still getting good estimates of sort of the probability that someone survives one more day given they're alive today. So you imagine that, here's what it's going to do. Basically, each month, you imagine calling everyone up. There were 1,000 people. In the first month, 2 people died and 3 people left the country. So the death rate in the first month is either 2 out of 1,000 or it's 2 out of 997, but it doesn't really matter. It's about 2 out of 1,000. But now for the next month, you know you have 995. So the next month, you know the baseline. So every month, you're getting pretty good things, and now you chain them together. And that's what Kaplan-Meier does. So we can connect this to the auction in the following way. Think of a particular person we care about, Orange. Okay? So let's think of xt as Orange's bid, and yt is the max of everybody else. They're independent draws. Orange's bid, the max of everyone else. Those are 2 independent things. And we just care about Orange. We get to see whichever is higher. We get to see either Orange wins and Orange's value, or everyone else's, somebody else won and their value. And so it's exactly this scenario, except first has become highest. Right? So xt is Orange, yt is everyone else. We can use that idea to learn Orange. Yeah, so this kind of connects really well with what we want in the case where we get to see who wins and how much they bid. So here we don't get to see the winning bid, but we can participate ourselves. We can kind of try to simulate this. So we get to participate ourselves. We can simulate Kaplan-Meier. And just to get a high level, some of the key ingredients, what you can do is you can set a certain price and see how often a particular bidder I wins. You can raise that price to some p plus delta and see how that changes. You can also see how often you win at those prices. And from that, you can use that to estimate how often this bidder bids in that range, conditioned on nobody else bidding above p. So these three values allow you to estimate this statistic here, how often the bidder bids in that range, conditioned on nobody else bidding above p. You work that out. And roughly, this is telling you how often bidder I wins with a bid in that range, conditioned on the price being below p plus delta. So conditioned on nobody. So Kaplan-Meier was doing is kind of walking down from the top, and that's what you need to do. So conditioned on nobody winning above here, what's the chance that bidder I wins with a bid in this range? And this is the kind of statistic you need. And that's all I want to say about that. This is the challenge is the other challenge. You have to control the errors to make sure they don't blow up, because you can try to make the error smaller by breaking into smaller regions, making the delta smaller, but then you've got more regions to chain together, and it helps to do that, to view the error as having both the multiplicative and additive components separately, and that helps the induction work. All right. You can also handle the case of subsets or different numbers of bidders of each type, like maybe, like is orange a person or is orange like a category? Because I always wonder, like, what does it mean to say your value is drawn from distribution? Like, why do I have an independently different value tomorrow than today for a particular chair? Well, I don't know. It's not me. It's companies in a certain sector, or it's professors or whatever. It's a category. And so you could imagine every day there's 0 or more orange people, 0 or more green people, whatever, and they're drawn from this distribution. As long as the set that comes on, there's a distribution over subsets, as long as the distribution over subsets is independent of the draws of the values from the distributions of our values. So we can't handle is the case where person 2 shows up only when person 1 has a high value. Like, that's no good. The distribution over the sets that show up should be independent of the draws of the values. Okay, and you can address issues like this. In fact, I didn't really talk about the connection to mechanism design at all, but another thing you could use this for is, imagine you want to set reserve prices, but you're not allowed to set them on a per bidder basis. But what you can set them on a per subset basis. In other words, what you can do is say, based on the set of people that showed up today, say, I think I'm going to set a reserve price of $25. And then, so what you're trying to do is learn enough about the bidders so that given that a new set shows up and there's some distribution over sets that show up, you can from that say, all right, let me try to set a reserve price as a function of the set. And you can use this information to do that. Yeah. Yeah. So I mean, what's going to happen is we're going to, from this, learn something about the distributions of the bidders' values, and it'll turn out to be enough so that if you get to see the set that shows up. So let's imagine, right? So for this to be useful for mechanism design, you have to see the set that shows up. So it has to be a scenario where you can see, oh, it's bidders 2, 3, 5, and 7 showed up today. I think I'll set a reserve price of $20. Which is kind of equivalent to setting your own bid as a function of who showed up. You're bidding on your own. I'm selling this laptop, but I'm also bidding on it. That's at least the way I think of reserve prices.
You know the subset and then you can set it.
Right. But you want to do it as a function of the subset. Yeah. Some extended models, you can address the issue of items with a common value component. So imagine every item has a visible feature vector. It's a bunch of features. There's this really nice, it's this very nice red cart with all these features and blah, blah, blah. And wouldn't you, it was owned by, I don't know, whatever. Anyway, so whatever auctioneers say, it's fun to go to auctions. And bidders have an unknown common value vector, W, that describes the values of the different features. And their actual value on the item is the dot product of this common thing with this item vector plus their own personal offset drawn from some distribution. So you can handle things like that. And I mean, I'm not going to get into it. Let me just go to open problems. So I think there's a lot of nice open problems in this space. I mean, I think that there's a kind of a, what we want to do here is from observing the outcome of some interaction, try to extract out the different components of that interaction. So, and I think that's like a really nice direction. These are just, some results in that direction. In the first part, for instance, we focused really on priority-based allocation mechanisms because they were simple and they're also efficient to simulate. So if the allocation mechanism itself didn't run in polynomial time, there's no way your learning algorithm is going to run in polynomial time. So, but you could have other natural allocation mechanisms, and maybe one could analyze them. So these priority-based ones were just a particular simple example that they were incentive compatible and you could run them efficiently. How about other natural classes of valuations? Single-minded, unit demand. What about other classes? What about noise? What if these aren't precise? Every day is maybe a little bit different. Can you address that? The case of unit demand bidders, there was a gap between upper and lower bounds. And then the second part, can we go the other way and take this sort of distributional thing and add a combinatorial component? And that I had no idea. And let me just mention a very concrete open problem here, which I really like. And it's very simple to state, but I just don't know how to solve it. What if you cannot participate in the auction? So you cannot participate in the auction, but instead you see the price paid by the winner, and it's a victory auction. So here's the problem in purely mathematical terms. We have some number of distributions where that number is, say, 3 or 4. 2 is easy. Let's say it's 3 or 4. Okay? You press the button, and what happens is random draws are taken from each distribution. Let's say these are distributions over the interval 0, 1 with full support. Okay? So they're distributions over 0, 1 with full support. Press the button, random draws, independent draws are taken from distributions. You see the argmax, the index of the maximum, and the value of the second highest. All right? So you see the winner and how much they paid, which is how much the second highest bidder bid. Okay, so we know how to deal with the case where you see the index of the maximum and the value of that guy. But instead what you see is the index of the maximum and the value of the second highest. And you don't know who the second highest was, because in the case of 2 bidders you would know. But it's not 2 bidders, it's 3 bidders, okay, or 4. Can you recover the distributions? In fact, I don't even, to make this like really embarrassing, I don't even know whether it's identifiable. So I don't even know, like here's the simplest version of this. Could there be 2 different 4 tuples of distributions? They're different, but they produce the same distribution on observables. I mean, that can't be, but I don't know. All right, so that's it.
Questions?
Kind of noise that, for instance, in the first basic problem that you're thinking about, where you just had comparisons between these 2 items, then you can think of it as being something related to noisy sorting.
Right. So it would be nice. I mean, our algorithms, right. Okay, so the question, right, was about, well, maybe you could work on noisy sorting for that, right? So so I think it's not inconceivable that one could say some interesting things there. In fact, I think there's 2 kinds of noise that are natural. There's like a noise on the auctioneer's point of view and noise on the bidders. Maybe it's easier to just take noise on the bidders' perspective, so to make it how much they value. Well, okay, either way. So the thing that would correspond to noisy sorting would be a little bit more like noise on the auctioneer's perspective. In other words, take the case of just 1 item, and the auctioneer has an ordering over bidders, and then 2 show up, and maybe the higher one usually wins, but maybe it depends. Either it's noise like a coin flip, noise, or it depends on how far apart they were. And all these things have been studied in the case of noisy sorting. Maybe the chance that it's like two teams play each other, and depending on how much better one team is compared to the other, if they're really much better, it's pretty likely the better team wins. As they get close together, it's more likely the other way around. And that would be like noise from the auctioneer's point of view on the bidders. And you could also have noise in the bidders' values over items. I think all of these would be interesting. I think, yeah, I don't know. Yeah, I don't know anything there. So I think that,
The last problem that you mentioned. So suppose you need a distribution that finitely moving. So doesn't that put support of the interval well, it's just finite. Then you think about it,
I don't really, I mean, I don't know. Yeah, if you make it finite, then you have to just say something about ties. I mean, well, although, okay, we can make it, it's nice to think of, finite and no ties. It's just, you can't do it together. But yeah, so then you just have to define something. What happens then? I mean, we just tried, okay. All I know is in simulation, it does seem to be identifiable. But, I don't know any easy argument. It should be. I don't know.
So one thing I liked about your, in the first part of your talk, you were talking about predicting what the outcome was versus trying to identify what the structure was, which is important if you're potentially never going to get that situation arising. You can never potentially learn the order, but as long as you'll predict well because you don't have to learn the order of things you never see.
Right, yeah.
Are there other tasks that you can accomplish in this model that might, like, maybe I don't care about predicting what happens in some mechanism, but there's something else I want to know. And again, it's useful. I mean, I only see the things I care about. The things I don't see, I don't care about. But I have some other task in mind that's...
Yeah, that's a good question. So I don't know the answer. In other words, is there, maybe one could combine that kind of learning with maybe a mechanism design goal, for instance. Like in the second thing, we can kind of combine it with a goal of setting reserve prices that depend on the set that show up. And then you can argue that the kind of errors you're making, you're learning. So I didn't actually even specify in what sense are we approximately learning the distributions. We're learning a good approximation to the cumulative. So it could be that there's like a little blip in the PDF, but that you don't, but you don't quite get it. But the CDF you get all right. So and it turns out that's above this turns out to be enough to estimate these reserve prices. We never really thought about in this case, but I think that's a great question. When you combine that with maybe a mechanism design goal or some other kind of goal, and try to feed those together. So I don't know. It's a good question.
So when there is, for example, a tournament, let's say a chess tournament or any tournament, I mean, then the organizer can sort of select which subsets or which two players play a game. And then they can kind of decide that, I mean, so the ordering in the tournament is dependent. I mean, the organizer can sort of choose the subsets which play beforehand. But instead of like just one tournament, if we consider like a set of tournaments or lots of tournaments, then essentially it kind of becomes random. I mean, who plays who and their results. So, and also, I mean, the strength of each player has a certain noise added to it. I mean, so can we use some sort of this thing to I mean, kind of rank players and give them ratings or something like that? When we consider basically lots of tournaments and the fact that each player's strengths have some certain noise to it.
Yeah, okay, I don't know. I mean, I guess in some sense, the thing we were focusing on had to do with like these sort of conflicts where, you have this sort of set of winners and the winners kind of depend in this way on the conflict. So like a weaker player, someone who's lower in the ordering, might still win in a kind of a funny way because the person who showed up that was going to take what they wanted actually didn't get anything because somebody above them showed up and took what they wanted. And you get these weird like non-monotone things where somebody showing up could be good for you or bad for you. Like if someone conflicts with you and they're above you, it's always bad when they show up. If someone conflicts with you, is above you and they don't conflict, it could be good or bad. It could be good because they knock out someone who's conflicting with you, or it could be bad because they knock out someone who's going to knock out someone who's conflicting with you. And so these other things can happen. That was the kind of thing we were focusing on. I haven't really thought about kind of that type of scenario and whether there's any. It'd be interesting if there's something that one could say about that kind of scenario, but I just don't know.
All right, thank you, Avrim.
Thanks.